Hey guys, hold on. Let me just change our reference frame real quick. Hold on. Oh, that's much better. Okay, much easier. So, you guys have a whole bunch of problems to do for this solar system project. I'm going to give you a little bit of help. Of the 6 problems you have to do, I'd like you to come back to school on Monday after Thanksgiving with the first 3 done. I want to look at those real fast. I'm going to give you a little bit of the help that I think you're going to need, and we should be good. Now, all 3 of them have to do with the force of gravity, which we've already talked about, and you should be good with. But the force of gravity is something that it's a force that comes from 2 masses interacting. Let's call them M1 and M2. Now, these masses, any 2 objects, have to be separated by some distance, and we said that distance matters, and we're going to call that distance R for radius, how far apart they are. It turns out this is really important though, so we square it. Lastly, when Newton first came up with this, his universal law of gravitation, he said, it's not quite right, it needs a little bit of adjusting. These are the important things, but it's just not scaled the right way. So we just throw a number in there to make it the right size. That number we call big G. And this number we know, we've done some experiments, I've given it to you. You can cite me as your resource for getting it. And the number is 6.67 times 10 to the negative 11th. You have it written down a few different times, but I'll put it up as we go. Now the first problem you have to worry about, I believe, deals with finding the force of gravity that would exist on your planet for a 50-pound object. What I ask for is the weight of a 50-pound object on your planet. Now, first of all, we know 50 pounds is not a number we like to work with. We want to convert that to units, or that we usually use. So we want to change this into kilograms. That's something that you can do, and if you can't, look it up and figure it out. But what we want to do is figure out, on my planet, if I was to put a 50-pound object, how hard would I have to pull to lift it up? Well, the thing that you're pulling against is gravity. So if I know how much gravity is pulling down, I know how much I want to pull up. So really what we need to figure out is how much is gravity pulling down? Well, it turns out a few things are important here. Number one, since we're talking about the force of gravity or weight, it matters what mass I'm trying to lift up. In this case, a 50-pound object. You know that. The other thing you need to know is the mass of the object that's pulling it down. In this case, it's your planet. You've looked that up, so we know that. As I just told you, G is a constant. It's a number that a lot of people, including myself, have done experiments to find out, so we know that. The last piece down here, R squared. How far are these things apart? Well, I can take a 50-pound object and put it on the top of the Empire State Building, or I could put it in the bottom of a basement, at the bottom of a cave, or some kind of well. That doesn't really matter. When we talk about a planet, and you guys have different sized planets, but when we talk about an entire planet, the height of a building, the height of a mountain, the height of or the depth of a basement or cave is negligible. We don't care about it. So really, when we talk about how far these objects are apart, what I'm really asking for is how far from the center of your planet am I? And how far I'm from the center is really just dependent on how big your planet is, the radius of your planet. So if I know that, the radius of your planet, which you looked up, you should be able to tell me how much gravity is pulling on a 50-pound object on your planet. Number one, done. Let's talk about number two. In number 2, I ask for the acceleration of gravity due to this force. So we have this force pulling on a 50-pound object, but it pulls on any object. However, the force of gravity on me is a little different than the force of gravity on this marker. The thing that's strange is that both of us accelerate towards Earth at the same rate. We call that a g, and on Earth it happens to be negative 9.8 meters per second squared. It's kind of strange that this happens to be the same for me and the marker. So I have to think our mass, which is different, doesn't really matter. And it turns out it doesn't, and we can show that mathematically. Every force, according to Newton's second law, can be written as mass times acceleration. If we're talking about gravity, the acceleration due to gravity, we can call this AG. And the mass I have over here is the object that's moving, the object that gravity is pulling down. So on Earth, if I were to do this problem, M2 could be written as mass of Earth, and M1 could be the mass of my object. Well, over here, I only have one mass. This mass is the mass of my object. And if I look at my formulas right now, I can just skip this whole piece. Equal signs are like a bridge. And since I have two equal signs here, I can bridge that gap. And I can say that mass of my object times AG equals G times the mass of my object times mass of Earth over R squared. But what I notice, and this is the important thing that helps me, is that the mass of my object doesn't matter. So I can get rid of both of them. They go away. I can't write go to 0 because they're not 0. They just go away. But if I rewrite this formula, I get AG is big G times the mass of my planet. I had Earth, but you'll have a different planet over R squared. If you know big G, which you do, and you know the mass of your planet, which you found out, and you know the radius of your planet, which you found out, then you know AG, you are done. The last part, or not the last part, but the third part, the third problem I ask you to do, deals with this again. So let's write it up. FG equals big G times M1 times M2 over R squared. But this time what I'm asking you for is how much force, how hard does the sun have to pull to keep your planet in orbit? It is an astronomical number, but you can calculate it. All you need to know is big G, which you have, M1, let's call that the mass of your planet, which you have. The mass of the sun, we'll call M2, which you have, and I give that to you. The mass of the sun is 1.99 times 10 to the 30th kilograms. Kind of big. And lastly, how far apart they are, which you looked up. If you have all these pieces, you can find FG. All three of these problems deal with the same stuff. You've done it, you can do it now, and you should do it before you come back to school. This is a break from class, not a break from school. Work over break. Enjoy your turkey day. Gobble, gobble. And I'll see you when you get back. Take care, guys. Bye.